going over any slides today. As I mentioned last class, I plan to do a live demo sort of thing. So if you can all come up front, that would help you guys also get as much as you can out of it. I haven't decided exactly the sequence of how to go about this. So there's a few notebooks that are already out there that are pretty good. I ran all of those. I have the outputs for those, and I was thinking I could just pick a random data set off of what is it, Kaggle, and just do it right now. So I can either do that first and then go into um, the the ones that are built by other people. Um, I can do that second because that's more comprehensive. Or I could do it the other way around and start with those so you have some context of all the steps that are involved and then do it live. So whichever you guys would prefer is what I can do. So to give you some context, this is a dry run of me trying to do that um, myself. And there's a lot in this that is redundant, and the reason I'm doing it like that is because I picked Coco as the data set, which is something that was published with the intention of doing segmentation and object detection, and I'm trying to do classification using that sort of to demonstrate that you have the flexibility to formulate a problem the way you want based on whatever information you have access to. Um, so even with a segmentation data set, if you like explore it properly and if you have image level class labels, then you can do classification. That's the assumption that I started doing this with, and then turns out each image, since it has multiple objects, there's multiple classes present. So picking the one that covers the most area, I guess, would be the way to pick the class that would uh, be the most relevant for that image. So if it's an image of a bunch of people and there's a horse and uh, those are in the background, and then there's a really big fire truck up front in the foreground, which takes most of the space, then fire truck is the class that you would want to see for that. And the way I did the pre-processing for that doesn't account for that. So not yet, at least. And my plan was to sort of talk through it as I'm doing it, just to give a sense of how dealing with these problems in practice is like, because normally the context in which we're presented all of this is either when you have a well-structured data set like on Kaggle, or if it's code that goes along with a paper where they're using a data set and you already have model code and you just want to run it. And those are typically self-contained because you only care about that one step, and that doesn't fit in a bigger pipeline or anything. So um, I guess things that I want to cover today are the other stuff apart from the model architecture and just building and running that, but how to sort of load data and formulate multiple problem statements with the same data. That's what I was going for. And I think I'll be able to cover stuff until classification today, and then segmentation and detection I could cover next class maybe, or we could do that today if I'm fast enough. I don't know. We'll see. Uh, so I had up here just random Kaggle data sets, and I was thinking we could pick one from here, and then I'll just walk through my entire process. So that's one part, and then the other part is existing notebooks that are out there. I can the ones that I already ran, I can walk through those. So the sequence of that, I'll leave it up to you guys. So if anyone wants to vote on that, you can just say which one you want me to do first. Yeah. Yeah, the other notebooks. So I'll share links to these on Piazza. Um, Good morning. You run?
A bit. When I can. You?
I've thought about it a couple times. That's as far as I got.
I didn't, this was the only marathon. I had to walk, so I feel like kind of didn't count. Gotta do another one. It was a few years ago too.
I get gassed out really quick.
It's gotta run slow.
Yeah. Oh, sorry. Here you go. There we go. All right. Okay, I figured I'd write that down just to make it clear what the options are, or rather, so the agenda for today, I don't have any slides. I'm gonna do a tutorial session of sorts. There's two broad blocks I can break this down into. The first one is there's a bunch of notebooks with good code and it's got like markdown explanations, all of that. I already ran all of those notebooks, so there's outputs for all of those. The Udacity, I think there's 8 or 9 notebooks that demonstrate the whole workflow. Dr. Redmond's class, he also did 2 tutorial notebooks, which I ran, and I have outputs for those as well. So those I would just be sort of talking through, that there's no doing over there. And the other thing that I want to do is I'll just, or rather you guys will vote and or pick a data set from Kaggle. I'll put that up there and we can pick something and I'll just work through it live. Now, I'm not sure if I can finish that in the hour and 15 minutes that we have, but I will try my absolute best. I also did a sort of dry run of what that process would look like last night. And what I did with that was I took the Cocoa dataset, which was built for segmentation, and instead of using it as intended and using libraries that wrap around the dataset, letting you interact with it, I tried to do classification using that just to sort of demonstrate that before something is published and like made open source and shared, there's people who work on the raw data and like curate the data set, write custom data loaders, test out a bunch of models, see what's working, what's not. So yeah, to demonstrate that process is why I chose to do that. So what I would like is for you to do I put this up as a poll on Piazza that you guys all vote on really quick, or do you just want to throw out numbers? Do you want 2-1 or 1-2? 2-1? Okay. How many for 2-1? Uh, okay, okay. Yeah, I guess that does make sense that there's more value in that because I could just share the other notebooks directly and you can go over them yourselves. All right, so let's do that then. Switching back. Oh, I gotta do that over here. Portable HDMI. Okay, we're back. All right. I would like to start with classification because that's the easiest to deal with, and I feel like I should be able to finish that in an hour and a half, provided we don't have like environment set up, or these data sets look pretty small. So does anyone want to pick something from here? We're not doing the gender one. I don't want to touch that. Um, does anything jump out from over here? Who likes birds? Okay. Potato plant disease. I wonder what that's about. So yeah, this would be really simple, I think. 354 files. Dog breeds should also be straightforward, I think. And Yeah, between dogs, birds, and tomatoes. Any inclination? I got one for you. You said tomatoes. You said birds. Anyone else? Brain MRI. Ooh, that's a toughie. Where is it? Tumor detection. This if it's an object detection or segmentation kind of thing, then I'd rather not touch that now. Maybe I could do this next class. We'll have to see what the labels are like. No, no. Oh, I wonder if they're all, if they just say yes and no, then I think that should be simple. Oh, yeah, okay. Yeah, we can do that. We can classify this. So, brain, birds, tomatoes, dogs. This is a consensus thing now. You guys have to figure out which one. I'm not gonna pick. So make noise and arrive at a decision. You have till 10:41 on that clock. Okay, shift towards brain. Also, feel free to come up closer to the front. The only questions I'll be asking is whether you guys like follow what's going on, and it makes me more approachable if you don't get something that I do and want me to sort of expand on something. Someone say something? Yeah, what's up? Sorry? Dogs? Oh, okay, yeah, that's a fair point. Did that convince anyone to switch? Dogs? How many for dogs? Let's see hands. Not a lot of numbers, you guys. Um, three, and I think we had more interest for the brain problem. So unless you can convince people to switch, I think I'll stick with that. It's all the same to me. I don't care. They're images with labels. I don't care what's in them, really. So let's try to deal with this. Now, I'm not gonna spend time on the architecture, sorry, the environment setup stuff because that it takes a while to do all of that. But I like PyTorch, and that's what I'm gonna be doing. But the broad strokes of how to set it up. Now I have ideally I'd also be doing this in Linux, but I don't really use this computer for much of actual work. This is just for PowerPoint mainly. Okay, so first thing to know is whether you have a GPU or not, which hopefully if you were involved in the purchasing process, you would have some idea of what kind of hardware you're running. I have a 3070, which has 8 GB of VRAM. So this it does the job, I guess. It's not great. You're not gonna build anything state of the art with something like that. But it yes, yes, very much so. Half of what I tend to have to help people with at my lab is just dealing with CUDA. It's a real pain. I was trying to do something yesterday where I needed Open3D for Python, and that was not there was no binary for the version of Python that I was using, 3.10. So I ended up having to build Open3D from source. Took me all day. Um, Not fun. Uh, CUDA installs and stuff also generally it's a lot easier to manage that stuff on Linux, but and if you're doing it on Windows, I would recommend using the Windows subsystem for Linux because that lets you run a sort of it's kind of like a Docker container, I guess is how I would describe it. It's a sort of GUI less self-contained Linux kernel instance that you're running. So I would get it from here. Conda, I usually prefer over doing things directly with pip because it sort of keeps track of what depends on what, and the odds of you ending up with a broken installation are smaller. Okay, so first step was downloading the data set, and I'd got to find where that went. Okay. So we have that over here. Just gonna extract that really quick. And what is this called? Brain MRI. Okay, I'll just call it that. Ooh. Right. Brain tumor data set. Yes, no, this is structured a bit weird. Because ideally, this is like train or test. We'd have to see if there's documentation for that. So first priority, I guess, is just understanding what's in the data. So I'm gonna go ahead, start a new notebook. Actually, I'll do this in a different folder. Let's see. See. I'll just do it on the desktop. Live. Okay. And let's copy over the data set. Is this it? Yeah. And put that in there. Now I already have an environment that I built earlier, which I know will get the job done. So I'm going to stick to using that. Activate, what do I call it? CS3. So this, I've made some changes to the environment. It's a bit different from the version that I shared with you guys earlier. The main difference is that it now has PyTorch in it and a bunch of CUDA stuff. Archive. Just want to double check the structure of what was within the zip before I get started. Okay. Oh, so that is how it is in there. That's weird. My guess is that it would be a train and test split, maybe. Trying to see if there's any documentation for this, which I can't seem to find. Yeah, I'll just load up one of those first and then we can figure it out as we go. So classifier, do stuff in Jupyter because it's easy to sort of test things as I go. First thing that I'm going to do is just get all the file paths and stuff and sort of try to see what's in there. There's a bunch of ways that people do this. This is the method that I like. It doesn't really matter what you do as long as you get all the file names and paths. So Glob does pattern matching for file names and directory names and stuff like that. I should rename that to data just because it looks better. and it's more descriptive. Okay, so we have that. I'll call this inner paths just to be just to have both of them separately. Inner paths is that glob. So wildcard for brain tumor dataset, then another one for the class label, and then whatever the actual format is, which is JPEG. Net sorted is what I imported. Okay, and then outer paths is almost the same thing, but with one less wildcard. Because we're trying to find these. Okay, Y1, these are named a bit different. No, they're not. Y1 over here is that. Let's see if that's also the same here. Yeah, they're the same. So I guess it's redundant and it's not a very well-made data set, I guess. We'll find out. Inner paths, data one, no, okay. Feel like there should have been more there. Are they not all JPEGs? Oh, there's some JPGs also. So this, if I had done os dot list dir or something like that, that would have returned all of them. I like doing this because the kind of data that I deal with usually has multiple formats, and I just like knowing exactly what I'm looking for. Okay, so that has a lot more. Let's just check how many images we have in there really quick. Do that for both. 3. That should not be the case. So, oh, right, yeah, because we have this one. This will go into, oh, I think I should be doing 4 here and 3 here, accounting for data. Let's see. Okay, yeah, that looks closer to what we would expect. Okay, another quick check is what is not in that. There's a way to do that. Set outer paths dot disjoint. Okay, that is not doing what I thought it should. The other way, let's see. So outer paths has 2 more. So path 4, path in, outer paths, if path not in. So that should, oh, that's, oh, okay. So it's these two that are different. All right. Maybe I should add the JPEG somehow in there. And just check that we're getting exactly what we need. 251, yeah, both of them match now. And this should be empty. No, they won't be empty. Because if you look at what the actual paths are, because they're at different levels, even though the file names are probably the same, the path leading up to it is different. One node, data node, okay. So for that, what we can do is this, and then change this to do a little bit of pre-processing on all the paths. Inner paths equals path, absolute path. So we're resolving all the paths. for both, which means that they should be identical. If not in inner paths. And we get the base name, which gives just the file name. Base name. And yeah, so at this point, I'm certain that they're all the same files in both of them. So we'd be okay looking at either one of those because does everyone follow what I was checking so far? Just that all the file names are the same. So I extracted just the last part with base name. Okay, now I guess first thing to do would be to just look at what all of those are. And I will also, okay, I'm not going to use a data frame. Let's not complicate things. We need file name and class relationship. So I make a dictionary and iterate over all the paths, and then would you prefer that I do this without Copilot? I feel like disabling Copilot, I'd still be doing the same thing, but it would just take me a bit longer, and the odds of me being able to finish in an hour and a half reduce. I could still try it though. That doesn't make much of a difference to me either way. Let's give it a whirl for a couple of minutes, and if it bogs me down, because I haven't turned it off since I turned it on, and it's been a while since I started using it. Guess we're about to find out whether my abilities have atrophied from not doing it myself. Okay, so file name, class map. We want file names to be our keys and our class to be the value. So let's take just one path and look at what it is. Inner path, I have the first one open. Oh, that's not good because I replaced it. Oh, okay, that's helpful. It's got it in the name. So that saves us a bunch of trouble then, because we can just pull that out of the file name while we're passing it to the model as part of the data loader. But that's not really good practice, and we also want our code to be a good sort of self-documenting representation of what we're doing in terms of pre-processing. So the fewer things that are implicit, the better. Okay, so there's nothing to split here really, because that's what the path looks like. I guess for each path, if I just check if no is in path dot lower. I'm doing that because I don't want to assume that all of them are lowercase. Then I'll say that label is 0. And I could just say else one, but I also want to catch the case where that isn't present. So failing explicitly is better. If, okay, do all of them start with a Y? Let's check. Okay, that seems to be a fair assumption to make. So that starts with, I think that's the, or is it begins? I don't remember. This is the kind of stuff that Copilot really comes in clutch with. Starts, yeah. Okay, so it didn't know that that was a string, which is why I wasn't getting that completion. So by wrapping it, I got that. If it starts with an uppercase Y, then I know that the label is 1. And then I can put that in my dictionary. and say path, which at this point, so I should call this file name because I changed them. File name. And also Control D lets you select something and spawn multiple cursors where that matches. So that's what I just did. I have 3 of those now. Can also use F2, I believe, to rename a symbol, and that change propagates. So file name equals label, and I'm missing an equal there. And once I run that, I should have my map ready. Okay. So next thing to do is visualize it. PyTorch generally likes PIO image format. So we're not going to use OpenCV for much generally. I'm going to take, what did I call my paths? Inner paths, okay. Actually, I should also hold on to what the prefix for inner paths was, just in case. And I get relative path, and put that there. This R is something that I have to do because I'm using Windows, and Windows uses backslashes in its path strings, which other OSs don't do. And backslashes are generally problematic because they're used to escape stuff in strings. So, oh, what happened there? Was I supposed to? Okay, whatever. Inner prefix, data. Do I? No, that's not a good idea because there's both yes and no in there. So instead of that, I'll do it down here. Data root is the folder called data, and then our classes are, what is it? No, and yes. So I should be able to use that in iterators maybe later. I'm just leaving that there for now. Not going to do anything with it. Let's pick one sample image path, call that data root, followed by, oh, we should do one of each. So I'll put that in a for loop. For class in, oh, class is a keyword. So call that class name, classes, and then yeah, I'll do the list directory. Okay, I'm gonna enable Copilot this because I'm going on a lot of tangents without that. How do I turn it back on? Enable completions. Okay, all right. Data root and class name. So we're computing that also, and I want to see what files are in there. So I do list directory and pick the first result from that, which gives me an image path, and I'll image dot. So I'm loading up the image now, and I'm throwing in a convert RGB just to make sure that everything's always 3-channel, because you might end up with 4 channels or grayscale or whatever in between, and it's just better to have everything in the same format. And I think if I do that, it should show me one of each. but we'll see. Ooh, anti-path. Okay, so this Windows doesn't play nice with that, I guess. Image open, let's do glob instead, and just pick whatever image is in there. Okay, so that should have opened too. Guess not. So let's do it manually. Mat board, matplotlib to display stuff. PLT show, and we create two figures just so they both open up. Wonder if I need to close it. Oh. This is weird. And normally that would open in my notebook. I don't know why that's doing that, but not much I can do about that, I guess. What is up with our paths? Last name, yes, no. JPEGs, data. So, no and yes, weird. Okay. So I'm doing all of this stuff beforehand so that it makes it a lot easier for me to write the data loader when I have to do that. The other way that I could try to do that is skipping all of that. Torch vision. Okay. Always have to look at documentation. There's no shame in doing that. Image folder. Okay. So this is in Torch Vision datasets. That lets me wrap a folder. So this is going to be the whole data set because it's not split. Data root. And I'm also going to add in the folder after that, simply because there's these three folders at the same level. So if I pick that path, then that makes stuff less ambiguous. I'll just pass that in directly. And what happened? Oh, backslash classic. Okay. Data set. We should be able to see how many images are in there. 253. Is that right? 251. Something doesn't add up. Let's see, data set. Well, what does it have? Classes, no and yes, that's fine. What other attributes does it have? Samples. Okay. And it also has a label going along with it. So this is the format that images get loaded in generally as a tuple with your input and label. So that's all nice and handy. The other way to do it when you're dealing with here, it's easy because you're just loading up images that are saved directly, right? But if you have something that you're getting from, say, an MRI machine or LiDAR or whatever, that will typically be in some sort of 3D array format, and you'd have to iterate over it, getting each slice and then load just that part. There's, again, design choices to be made over there. You could choose to load the entire thing into RAM because then moving it back and forth between the GPU is faster. But if you have a really large data set that doesn't fit in RAM, then it would be better to sort of pre-process those arrays and save each cross-section separately so that you can load them at training time, which then shifts the bottleneck from your RAM capacity to your IO read-write speed. So just choices to be made. In cases like that, you would write your own data set, which is generally pretty common. Data set is the class that this inherits. And that has three major methods. There's an init, where you sort of pre-populate all your file names and whatnot. Then I'm just gonna let this do its thing and then talk about the remainder. And I'll look at that in a second. The other main method is the length, because over here I was able to wrap it with len and get how many samples are in it. So that functionality is something that you would need to implement typically. And get item is what gets called when you're iterating over the data set using a data loader, which I will do in a second. And that's how you pass stuff to the models. And this is the main one that we care about. So this looks like it should be right. I imported data set. We have our root path. Transform is also something that I'll talk about in a second when we get there. So this is getting all the file names, getting a mapping between file names and class names and labels. So from string, yes, no, we need to represent them as numbers, which is similar to what I was doing earlier up here. And labels, okay, here, same thing again. We're sort of wrapping all of that individual logic that I was doing in separate cells over here, loading an image, converting it to RGB. That becomes part of, because we do that for each image, right? We're loading it. So here we're not saving the entire data set, pushing it onto RAM directly. This is doing one file at a time. And I'll run that. Cannot import data set. Oh, yeah, that should not be uppercase. All right, and this should do the same thing. Data set, I'll just call this custom and put that over there. And let's look at the length. Data set custom, and we have 253 samples over there. So the other thing that I said I would talk about was the transform. Now, to supply something to a model, it needs to be in a format that the model recognizes. We're dealing with PyTorch. So actually, I'll just load up a pre-trained model and then we'll play with that a little bit. Import, I'm going to get MobileNet because this thing is easy to run. It doesn't have a lot of parameters and it's pretty small. Okay, so I have the model. There's a better way to do that than saying pre-trained equals true. I think you're supposed to do something like MobileNet. Yeah, this small weights, that's an enumerator that you would then supply here. Saying weights equals, yeah, something like that, I think. But yeah, I'm not gonna deal with that now. That has more to do with just sort of being production ready or whatever. So I'm not gonna worry about that. What did we have there before? Pre-trained equals true. So I have a pre-trained MobileNet. We have a data set with a bunch of images now. Okay, we've talked about model architectures and stuff. Is there Does anyone want to share any insights that jump out, or any idea of what we would have to do first? What should our couple of first steps be with the model? The objective is to put an image in there and predict something. Okay. Okay, good. I'll put that down here in a markdown block, call it to do, and then resize input. Yep. What else? Yeah. If there's anything else, I want someone else to say something. If anything else jumps out, make sure output shape is right for the number of classes. And in our case, we have 2 classes. Well, let's get started on that part, and then if anything else occurs to anyone, interrupt me, and I'll add them to our to-do list, all right? So to resize our images, I think I know what the expected size is for this model. It's 224 by 224, I believe, either that or 256, which is usually what they tend to be. So we want to do that for every single image. And a good place to put that would be as part of the get item pipeline. So what we're going to do is we'll create a transform and then supply that to this guy here. And let's call that, we'll make separate ones for train and test, because that gives us a bit of flexibility. So before that, we need to import the transforms, which are in torch vision dot transforms. Oh wait, this is, yeah, okay. That was a markdown block. Port, actually, transforms, import v2 t. You can just import transforms also directly. This is something that's probably transient and will go away at some point. But the way transforms are represented are as a pipeline of operations that you can apply to each image. So we can choose to crop some part of the image and then resize it. Random resize crop here will randomly select some region from the image and then crop that. Horizontal flipping, it's doing it. So these are augmentations that let you make your data set more varied by artificially introducing changes to your data set in a way that doesn't change what class it is. But we're not going to do that just yet. Let's just stick to resizing it for now, and then we'll see how it does with the model without doing any of that, and then we can improve things if time permits. That is, this has to do with the intensities you typically see in like color images, RGB channels, natural like ImageNet type of images. So that's a very good point, because we're dealing with brain MRI images, which look like this. So applying that sort of normalization here would be very bad. And I'll take that out, but I'm glad you brought that up because I missed that. Train transform, let's apply this to our data set and create that again. Data set, custom. I don't have to create a separate object again. I could just like reassign the old one, but just to have it out there separately. Now to get one sample from this, what I can do is wrap it in an iterator. This is a very crude equivalent of what a data loader would do. And since my goal is just to see what is in there, I'm going to check its type really quick. This should be a tuple. How many elements in the tuple should be 2? Oh, 3. That's interesting. Why is that? Oh, it also returns the file name. We don't need that. So I'm going to take that out of here. We don't really care about the file name. Okay, just rerun all of that stuff quickly. All right, yeah, so now we have our image as the first part of the tuple and a label as the second part. So let's see what it does when we do the normalization. And I think, oh, my Matplotlib was broken. I don't know if this is going to work, but we'll find out. Sample. Okay, we want to see just the first part of that. And yeah, so that changed what it looks like, and that's because of the normalization in there. So once I take that out, this will look the way we want it to. That's what it actually should be like. And this permute that we do over here is because when PyTorch gives you that element from the data set for images, the convention that it follows is channels first. So we got to move the channels back to the end so that Matplotlib knows what's going on. So there's the 3 channels up front. Even though it's grayscale, it's basically all the same information in 3 channels, and then height and width. So this resized it to 224, which is part of our transform pipeline over here. Now that there's one thing we haven't done yet, and it has to do with the data set. Does anyone want to guess what it might be? What would happen if I threw this data set into the model directly? I'll come to you in a second. I did not split. Yes, that is exactly what we have to do. So if I just threw everything into the model, I have no way of evaluating it against something that I haven't seen. So I'm gonna split that. And I think, yeah, 80% is generally what you see. And I have to assign this to something which I forgot. Train set, and then what's called test set. So now I have 2 of those, and I can wrap them in data loaders. So what a data loader lets me do is a couple of cool things. I get to shuffle my data set. I also get to load batches of images. I get to do that using multiple threads, which you have to tune that a little bit to find the sweet spot, but that makes the whole training process a bit faster because they're able to read from disk faster. This I'm just going to keep it to 1. We don't shuffle, and batch size I'll also leave that at 1. So now we have 2 data loaders. We have a model that we defined somewhere earlier. Yeah, got a model over there. So I'll show you. So let's look at one batch of samples from the train loader and look at its shape. you'll find that there's a fourth dimension now. So there's 32 samples, 32 images, and the same will be true for the labels also, which will be in batch 1. So this should be 32 comma 1, I believe. Yeah, it's just 32 because it's a single vector, and 32 comma 1 would still contain the same information. And test loader will not have 32 samples, it'll just have one because I set a batch size of 1 over there. Now, to pass it to the model, okay, there's still a couple of things on our to-do list remaining. So let's look at our modules in the model. And that's a generator. So I convert that to a list so that it computes all of the elements of the generator, and we should see what the names are. So this has the whole model architecture, and I only care about what each module is called. So I think if I say keys here, because it's kind of like a dictionary, no, it's not. Let's look at what's at the end. Oh, that should go outside. Okay, yeah, so this is the part that we want to be changing. In features is, this matches whatever comes out of the layer before that. So if I look at that, and I don't know if it's going to let me do that. Yeah, okay, so there's this average pool before that, and then there's this whole feature extraction block. So they're bridged by average pooling, and the output of average pooling will have whatever size that was, 576, I think. Yeah, and there's a hidden layer after that that has 1024 weights, and there's an activation in between dropout, which randomly discards 20%, or rather neurons with a probability of 0.2. And that goes out. So this is the final output that we get from the model, and there's 1,000. So this was built for classifying 1,000 classes, and we only have 2. So we want to change that part. I'm doing it this way because I started with a pre-trained model. There's another way to do it. I'll do that after this. And if I forget, maybe someone can remind me. Model, so classifier, and we want to change. Okay, I think I can do that. Yeah, and we replace that layer with another one. So port torch.nn and reassign that. So this is 1024, and we have 2 classes. So a better way to get this would be train dataset. If our dataset had a number of classes object, that would be the ideal readable way to do it. I don't remember if we did that. Class names. Okay, yeah, we can infer from that. So this dictionary, however many keys it has, is also however many classes there are. That's one way we can do it, I guess. What was that? Train dataset, what did I even call it? Train set, okay, there we go. And what do we have in there? How are we doing? Oh, wow, it's almost, I didn't realize we were almost out of time. Okay, I'll speed it up a little bit. Model classifier. So then next step is to iterate over the data loader itself. So for image batch and label batch in train loader. So that unpacks every element from the train loader into these two. So what I was doing earlier here with train batch 0, train batch 1, implicitly that happens over here and directly gets assigned to both of those. At this point, we haven't trained anything. This is just a raw prediction of what we get. Mat 1, Mat 2, 576, and 1024. What happened over here? Hmm. So something doesn't match with something else. Think where's our architecture? Let's look at the model once more. In features 1024 over here. Sequential 316. So there's 16 filters, 3 channels, kernel size of all of that. That comes down here. Activation. Okay, so this is spitting out 576. That makes sense. 32 by 576. What would that? Oh, so I have to factor in whatever the bat size is into that in features size over there. So let's go ahead and this would be 576 times what was the output? 576 channels. And this is easier when I define the model myself. Actually, I think there's a better way to. Okay, this is full disclosure. There's a kind of thing that I tend to have to look up. But linear 124 2. So can we look at last layer output shape B model classifier in features? Okay, I'm just gonna it doesn't do it. And number of classes and also batch size. So if I include that here, size, then I think I'm missing something. Word. Suppose, hang on, I need a minute to think through this model. One batch, this should still give me the same issue, I think. Let's see, okay. So equals model dot features, and then equals modeled average pool, and then we look at shape. There we go. Yeah, I believe that should do it. Where's my print at? Let's go 32 by 576. How much is that? 18. Okay. Did I not do that? Oh, right. So this is, we'll call this average pool output. I'm not very good at math, as you couldn't tell. And let's get that in there. And so we okay, so we have 32 times 576. So we can take and there's a way to I know there's a better way to do this, but one, and that will reshape it. And I think that should take care of it. Okay, now what do we have? 10 for, oh, okay, okay. So our input number of features now has to match that. So we're one step closer, go to our, size, so we're calculating that. We do just if find input size. This is gross, but this is how I usually do it. And I think if I, yeah. Okay, so that should run that once as part of setup. And assign a value to FC size, and then I can take that and put that in here. So I'll move that above and I really hope this works. It's been okay. Storage. Okay, so what I'm doing is I'm just passing a random tensor through the feature extraction and average pool part to get the size. That's probably there definitely is a better way to do it. I just can't think of that off the top of my head. Oh, come on. FC size, what is it? Okay, so this would be a part of standard transfer learning pipeline, but let me just define a simple thing really quick. And then module convolution maximal. Let's see if this runs 512 number of classes. So here all the shapes are like known in advance. This should be simpler to run. Simple CNN model. Number of classes is 2. Now we find out what device we're going to run this on. So if I have a GPU, it's CUDA. If not CPU, this part I'll figure out and share a snippet or whatever later. Just want to get done in time. So I have a GPU, so everything's going to run over there. Now for image batch and all of that. First thing to do is make sure everything's on the same device. It's also going to crib a little bit about data types for each of those, but we'll deal with one problem at a time. First thing to see is just if we're able to get an output, just forward pass. So one of them, input, is a CUDA float tensor, and weight is just a float tensor. So that should tell you weights are part of what? Weights are, yeah, they're on the CPU, but like, what is it that we need to move to the GPU? Your guesses, even if you're not confident, if they're louder, then I can hear them. There's a few choices that we have. We already know that our input is on the GPU. Weights and biases are part of the model. Those are not CUDA tensors, so that logically the model is not on the GPU, and that is because we didn't move it. So model.to device that moves it. We want to set it to trainable, which we do in here typically. So we got some output of 32 samples with 2 values. Let's look at what those are. So this is the output for one of them, and we have just 2 values that it predicted. So this doesn't have any activation before it, no softmax, whatever. It's just no sigmoid either. Now to train it, we are missing a loss function. This is we're doing classification. So anyone want to guess? And we also need an optimizer, for which I'm getting Atom, and then what loss function do we sub there? Cross entropy is multi-class. We'll try to use binary cross entropy. There's some nuance in the implementation, which I always have to check, because one of them has the sigmoid as part of it and expects raw logits without any activation, BCE loss, and I think the other one is BCE with logits loss. Let's look at loss functions. For classification, we would care about cross entropy. If there's more than 2, there's BCE, and there's BCE with logits. Yeah, this combines a sigmoid because we only have 2 classes, and this is that they do something under the hood which makes it better. So this is preferred. We're going to use that one, BCE with logits loss, and instantiate those. So create an optimizer, create our loss function, and then we want to keep track of what the running loss is and the initial loss. So import math. Loss is, and now, okay, so this is for one epoch, right? Because going over the entire training split once is one epoch, and we also want to do this for multiple. So I'll say let's do it for 5 epochs and another loop around that. So this will do that for 5 epochs. Now we take here, running loss 0. Now with our outputs, we calculate our loss. And oh, wait, that should not go there. I think should be zeroing the gradient somewhere else. Yeah. Optimizer, did I not create that? Thought I ran it. Hang on. Okay. Well, still doesn't recognize that. But anyway, so you want to zero this before you calculate your loss, and then you propagate it backwards by calling backward on loss, and optimizer step does the learning part using that. So we do that for every batch of samples that we looked at. We calculate loss and propagate that backward, and increment the state of our optimizer that gives us our weight updates. So yeah, at the end of each epoch, we can print that. We can also print that for each sample, which will be really noisy, but I'll do it just in case. In any case, I'll put a couple of breaks in there so that we don't run the whole thing. That should do something. Target size must be same as input. Okay, so anyone figure out what the problem is? Our label format is 0 and 1. So that is something that we would supply to a single neuron rather than 2. In this case, since you put 2 neurons in the output when you want to account for the possibility that both classes could be present. So for multi-class, if you're sure it's going to be either or, then you would have 1 class at the end and use binary cross entropy. But since this is the way I define the model, I'll swap that out for regular cross entropy. Ideally, I should be doing it the other way around with 1 neuron at the output and binary cross entropy, because if there is a tumor, then the no class cannot also be true simultaneously. Basically, having 2 neurons opens us up to the possibility of getting 0, 0, and 1, 1 as our predictions, which are not possible. But in any case, we need to one-hot encode our labels so that they can be supplied to that. So do I already have functional? No, I don't. So I need to import that torch dot functional as f, and for each label before I move it, label one hot, and then one hot encode them into 2 labels, and I move label one hot to the device instead and reassign that to label batch. So now we should be able to calculate loss, since the shapes for both of those would match. One hot and encode. Okay, torch functional one hot. Oh, it's in nn dot functional. Okay, so nn dot functional, and I gotta change this back. Float can be cast too long. Wait, what part is this at? So criterion, level batch. All of these need to be floats, I believe. So let's just quickly convert that to a float. Convert these also to floats. What else? Labels. And yeah, I think that should take care of everything. Okay, so we got a loss value. Now this doesn't really have anything to do with neural networks or whatever, but it's just a cool way to keep track of what you're doing. This gives us a progress bar, which is very neat. If you're an antsy, restless kind of person like I am. Train loader. Okay, so just wrap it and it figures out the rest. I'll also do that over here. And I'm gonna take out the break from the outer one. So this will run for one epoch on the whole data set. So we started at a loss of like 2, and that's fluctuating a little bit, but seems to be doing something. I'll let that run for a while longer, and I'll get a. So since I defined the model earlier, this is, if I ran this again, this would continue improving since it's not starting from scratch. I'll just do this part again, just to be more faithful to the experiment. Reinstantiated the model, move it to the GPU, and I think everything else is already taken care of. Just move this part also down here because the optimizer also is stateful. And I don't want to interfere with that. Okay, loss, whatever, running loss. All right, let's see what that does. So ideally, we should see this go down a fair bit. Oh. So that's the sum of the losses of all batches that we looked at. Does seem to be going down a little bit. We started at 7.6 something and it's gone down to 319. So let's try to run this for, let's say, 50. Let's also add some logic to stop this best loss. Let's, yeah, get rid of that. And then, okay. Now, if running loss is lower than the best loss, and we also need a patience, early stopping, yeah, for 5 epochs, that should be good. So increment that, if not, stop. Now I suspect that this should stop before 50. We'll see. So what this says over here is that for 5 epochs consecutively, if the loss value does not decrease, then we stop training. And we'll see if that happens or not. I think it might just keep going for a while. See, that's the good part about wrapping it in TQDM. You get some sort of an estimate of how long it will take. 2 minutes, I think we can all spare. Yeah. Any questions? Yeah, the other one I couldn't just like doing this here live. Uh, it's harder than sitting at my desk and doing it myself. So I wasn't able to think through it. For the next homework, what I was thinking is transfer learning, probably. So in this case, we had to figure out the size of what was going into the input layer for that model, since I think there was only one fully connected. Oh, right. Yeah, I remember now. Let's just do that while we're at it. Where's the mobile net? I'm not gonna let that best me today. Mobile net v3. Okay. Let's get one of these and mess with that. So what I was doing was replacing the entire like last block. Instead of doing that, if I just change the last layer, then we'd be fine, I believe. Let's call this model 2. Is this done? At 38. Yeah, it stopped at 38 because loss is not going any lower. And at this point, we'd want to compare our predictions with what the ground truth was. So I should have held on to all of those, which I didn't have the foresight to do. Here, output. So if it's, I typically do epoch, spreads, epoch labels, and then we take our outputs and append the output to it. Labels, yeah, these are one hot encoded. Okay. So at the end of each epoch, we'll have spreads, which we concatenate and then print accuracy. Basically, just check if they're equal or not. That's about it. So I'll run that in a second, and you'll get to see how the accuracy also changes. But before I do that, model 2, let's see, model 2 dot. How do I get the classifier? And if I just get the last layer from this, oh, okay. Feel like changing this. Why is this giving me 1280? I don't understand. Millimeter. This should have been the exact same. Model 2. Move that also to the GPU, and then model 2, and then image batch, because we already have one batch. Yeah, so that worked. Earlier, what I was trying to do, I think I was messing with, I don't know what I was doing wrong. I'd have to go back and check. So here, basically, I subbed out the last layer with, initially it was 1024 going to 1000. I replaced it with 1024 going to 2, and that works with our current dimension. So I can for yeah, epoch, running loss, all of that, and just do this exact same thing with model 2. This might be a bit slower, probably. No, it's not. Okay, 55% initially. Got a bit worse. Okay, we're up to 60 now, and it should overfit after a point. 54, it's hovering around that. So in this case, we'd have to maybe add another layer before this, or figure out why the simpler model was converging faster. Um, I'm just gonna go back up and rerun the other one so we can compare. And I'll stop there after that. Oh, that looks, oh, this is the old one, sorry. 55, 56, yeah, it doesn't, oh, this is on me. Of course, it's not gonna change because I never set the model to be trainable, I think. Yeah, I didn't do that. So model to dot classifier dot one dot parameters, or actually, yeah, for in parameters, we want to set those to trainable, because if not, it's just going to be doing the forward, and everything else needs to be frozen to the pre-trained. Actually, since they're not natural images, I guess it makes more sense to just fine tune the whole thing. So I'll get rid of that. And now I think we should start seeing some changes. Mm, 4.76, 4.83. Okay, we have other problems, I guess. 1, 2. So this is our model 2, which we ran earlier, 76, 86, 96. What am I doing here? Something is off. Image batch, running loss, frame loaders, right? We want hot encoding it. Oh, image batch. This item. Are we not resetting the gradient? Yes, we are. Loss going backwards. What model is this? Oh, this is running model 2. Okay. I wanted to accuracy 0.5. Okay, so this is getting worse. That's a different problem. I'm gonna interrupt this and go back to the other simple one that we defined. Is this it? Can't tell. Okay, this is the simple CNN, and so we had some success with that earlier where the loss really went down after a point. 65%, 73%, 76. So this is more suited for the problem that we're trying to do, simply because the kind of variation that we have between the images is much less than natural images. So the kind of features that you would focus on are also, again, different from what something pre-trained on ImageNet would focus on. And what we can do with that, just one quick last thing, visualize feature maps of simple CNN. So we also want to save the weights and load them. I have all of that stuff. Actually, what I'll share, I'll upload these to UV Learns or Piazza or something. So this is the version that I did yesterday when I was trying to do a dry run classifying on Coco. And I've done everything like step by step, and it's a lot more sequential compared to the way I did it now, where I was jumping all over the place a little bit. So I'll add more markdown descriptions to it, and then I'll share it probably tomorrow. So this covers most of the basic stuff that you would have to do, including writing a data set, building a simple. So here I started with just a feed forward network, which was kind of lame. Then another classifier, which had exploding. Oh, this thing is still running. Wow. So loss values here were exploding and getting really bad. So I added batch norm, which made things better. I'm not going to restart that. I'll yeah, share that later. Anyway, visualizing feature maps and stuff. Yeah, I guess I'll do that next class maybe. But our final simple CNN accuracy is 100%. So without also comparing this with our validation set, you can't really say how good the model is, because there will come a point where accuracy on the training set or keeps increasing, and on the validation set it starts dropping off. So that's the point where it overfits, and that's the point where you would want to sort of stop and hold on to the weights from there. But yeah, proof of concept, a very simple CNN that fits to a distribution that we have. Was this helpful? If not, then I could just go back to slides and talking about architectures and problem formulations, that sort of thing. Or I could next class continue this and cover maybe segmentation or something like that, or just like expand on this. Demo or slides. So you guys don't have to lock in and worry about quizzes, which is fair. I just hope that this helps. And the reason I wanted to do this is because there's a lot of notebooks that are already out there, and like the what is it? The onus of running that is on us typically, and I'm not a particularly motivated student. So if there's someone who does stuff like this on YouTube or whatever, that helps, because they're, especially if they're talking through the process, and that helps with the sort of like gotchas that you would run into when you're doing it, or just a sort of like sequence of thinking about it, what things you check for as you're going through it. So that was my motivation behind doing this. If you guys all feel like this served that purpose, then I'll do another one of these. And if I feel like that seems to be the consensus, so I'll stick to this, and maybe I'll try to plan ahead a bit more in a way that's sort of a hybrid of having some stuff pre-made and doing some of it live. Because I got through the majority of intuition of the sort of high-level process of building and testing a model. And then after this, if I have a bunch of stuff that's pre-made, you still know what happened in the steps leading up to those things being made. Okay, yeah, that's it. Thank you for staying extra. hope it was worth it. And I'll see you guys day after. Yeah.
Share like what steps are you following instead of like coding through it before that, so at least we can like go through it and understand like what you are doing, like how is it different, so like to learn better, because like right now like transfer learning and how to create a data set was a thing as well. So something-
Yeah. So this other one that I had, I think I have it open somewhere. Yeah. So this is the Udacity public code that they have, and this goes over the entire sequence of operations, visualizing tensors, seeing what types they are, building simple feed-forward networks, making predictions, and it has all of that. This is a very thorough.
Yeah, what is, like, just the steps like what you are following like before starting it, so that at least I would know that this is something that I
Oh,
can-
okay, okay. In my notebooks to have a sort of like placeholder titles of,
Yeah,
okay, in
like
this section,
the
I'm going to do
yeah, the
this.
ones that even homework, like these are the steps in Panorama that has to be done.
Okay,
So that's
okay.
the usual process. So at least I would like in this you have to create a data set. That's something that I didn't know that something is.
Oh,
like,
are you
these are the
saying
steps.
for the homework or for the next
For the
demo
like
that I do?
any demo that would really help. Like these are the steps that has to be done, something like
Hmm.
that. So I can go
Okay.
through like how I would do it, and then it's easier for me to like see, okay, if I was doing something that's not working, this is the usual way to do it.
Okay. Okay. Yeah, I'll keep that in mind for next class.